Stanford University.
I've left an audience of about 130 people at EPRI on a presentation on renewable energy. Fortunately, I was able to outsource it to another group within EPRI, and they are running that right now. And there's not a single parking spot at EPRI, so the SAP people are going to be a little upset tomorrow. But I wanted to take this opportunity to show you some tangible work that's going on in the area of smart grid. You hear a lot of hype, and there are so many conferences that if you laid them out next to each other, every living moment would be covering some smart grid conference or the other. And there are so many papers being written on the subject and articles and interviews. So the question first is, what is the smart grid? And the second question is, what is really going on beyond the rhetoric around smart grid? So first I wanted to introduce the Electric Power Research Institute because I think it's important for you to understand how we fit into the picture, and then I can tell you a little bit about the work that we're doing in demystifying the smart grid. So first of all, we're a nonprofit organization. We were founded in 1973 as a result of the fluctuating oil prices, and the utility industry felt very nervous that producing electricity using oil was not a very good way of doing it. So EPRI was created by our founder, Chauncey Starr, essentially to help utilities collaborate and do research in areas of the electricity production, transmission, generation, distribution, and then end use. And the main reason for getting that investment in a collaborative way was that the utilities found that they were not competing with each other. Each one had their own region, and therefore they could collaborate, and the research findings, they could all benefit from it. So that's what prompted the creation of EPRI. We're a nonprofit 501c3 organization. So if you give money to EPRI, it's actually a tax-deductible donation. And there are over 1,600 customers of EPRI worldwide. And about 20% of our business is international. And we do about $350 million in annual research. So we get membership fees, and then from those fees, then we do the research. So think of us like Gartner Group or IDC from that sense, except there is a very practical element to it too. We have labs, we do tests, we share our results with our members. We also provide reports, EPRI reports, which I'm sure a lot of you have seen, on a variety of topics dealing with all aspects of electricity production and distribution. These are our four sectors: generation, environment, power delivery and utilization, and nuclear. Power delivery deals with transmission, distribution, and end use of electricity. Environment deals with all the impact that the production and transmission distribution of electricity has on the environment, the water, the soil, the temperature, everything of that nature. Generation deals with all the non-nuclear ways of producing electricity. So all the fossil fuel-based fall under that category. And then the nuclear sector deals with all aspects of nuclear power, from the design of nuclear power plants to the construction of them, to the running of them, and then eventually end-of-life issues. So all of that is covered under that. And we have many, many projects going on at any given time, and they're funded by different utilities and vendors. Within the power delivery and utilization sector, we have something called the IntelAgreed Program. This is the program that focuses on smart grid. It is the part that brings the power grid and the communication network together. And we study how we can control parts of the power system using networks, whether it is low power, low bandwidth AMI network, whether it is broadband over the internet to control, let's say, an energy management service box in a house, or whether it is a wide area network controlling a transmission grid, or whether it is a distribution automation network that allows us to monitor the flow of electricity and the maintenance of the voltage. All those aspects are studied in the IntelAgreed program. We have a variety of utilities and manufacturers that are in this program, and we partner with many organizations around the country, public utility commissions and regulatory bodies like that, or consumer advocacy groups at the state and national level. So what exactly is the IntelAgreed program? The IntelAgreed program is actually a methodology. So the methodology is about identifying what are the requirements in smart grid. And how do you figure out requirements? You go to use cases. Use cases are like narratives. They tell you how actors need to transact with each other for a particular business application. For instance, you're a consumer and you want to get your monthly bill from the utility, and you want to see it online, and you want to see it at any time of the day. You want to see it on your iPhone. You know, these are all demands, and those demands behind them are use cases. You explain that there's a transaction between two parties, and you define an interface on which the transaction occurs. You explain the data that needs to be exchanged. That puts requirements on the bandwidth of the network that needs to support that. And you can begin to see that you can identify a series of requirements that would support that particular business, application, or transaction. So there are use cases available on all aspects of how a utility functions with customers, with independent power producers, within itself to maintain it, to do dispatch. All aspects involve these narratives. They're like little stories. And Southern California Edison has done a very good job of cataloging those use cases. And those use cases are now being put as part of an interoperability knowledge base, or IKB, that is part of the NIST reservoir. NIST is the National Institute of Standards and Technology. They were commissioned, and I'll talk a little bit later in my talk about how they've been commissioned to develop interoperability standards. You may have heard of that through the ISA, the Energy Independence and Security Act of 2007. If you look under there, under, I guess, Article 13, Section 1305, that is the legislative piece that gave NIST the responsibility to develop the interoperable smart grid. And so EPRI, as the first phase of that project, was contracted to develop an initial roadmap. And I was part of that activity, and that occurred between April and August of last year. So the IntelAgreed methodology was used by the first phase of the NIST project to identify what are the requirements. Based on that, looking at the standards that are out there for the smart grid, and then from the standards, figuring out where the gaps are, and then working with the standard organizations like IEEE, IEC, and others to make sure that the gaps are filled. So there is a process ongoing in this country, and other countries are watching the United States take the lead in this, because the smart grid that we are talking about is not just about having a solid-state-based meter in your house. That's just the tip of the iceberg. There's a whole infrastructure that needs to be implemented in order to support what it's promising to offer you. And then bring into this the energy service companies and everything else that, the Converges and the Enernox and the Tendrils and others, and you're going to see that this is going to be a very complex thing. This is not a master-slave relationship where the utility is the master with all the data and puts up a big wall and says, come ask me for something and I shall give it to you, like Google does or Microsoft does or Yahoo does. That's what they do. They've got a demilitarized zone, and they've got a bunch of servers sitting on the demilitarized zone. That's what they call it, right? DMZ. But they don't let you into their trusted assets. They populate those servers at a time of their choosing, and you just work off of those servers thinking you have access to everything. You really don't. It's a master-slave relationship. But in the smart grid, we will not have master-slave relationship. We're going to have a peering relationship. So for those of you who are networking people, you will understand what I'm talking about. It's a relationship of equals. It's not a relationship of, I got something you need, and therefore I'll give it to you when I feel like it. It's more like, I need something from you, and you need something from me. And so we have to create an infrastructure that respects that equal relationship. So if you're an independent power producer and you got a bunch of wind farms, and you need to provide electricity to, let's say, an investor-owned utility, you'll need to share what assets you have available to the utility. Similarly, the utility needs to expose when it needs that electricity from you so you can plan better. So this is a very, very complex, and that's why I wanted to confuse you in the beginning. This is very, very complex. And so that's great job security for tons of people for years to come. And so for those of you who are in college and are trying to graduate, get in this business, you'll be fed, and you'll be fed happy for many, many years. But there is, in all of this complexity, a plan. And so my job today is to help you understand what that plan is. And as Thomas Friedman talks about, there's this operating system in the world, and you need to get connected to it to be in the 21st century. Well, in the energy business also there's an operating system. It's not Windows, it's not Solaris, but if you don't connect into it, you always feel like an outsider. So today my job is to tell you what that is. The IntelliGrid methodology is the process by which the smart grid technologies are going to be implemented. You ask any major utility today, how do you decide what to deploy and when? They'll eventually come back to the systems engineering methodology known as the IntelliGrid. They'll call it a bunch of things, but ask them, where did you get that information? Ultimately, it came from EPRI through this program. Because this was done back in 2001 and 2002 when nobody even knew what smart grid was. But there was a need to have intelligent systems. Okay. We have a bunch of research programs. I handle D&E, which deals with the customer interface and the cybersecurity aspects of the smart grid. And we have other people who lead the other project sets. But all of this work is now being provided to NIST. It's being provided to the Utility Communication Architecture Working Group. It's being provided to IEEE P2030, the IEC groups for SIM, and for 61850. All of them benefit from these research findings. So this is the diagram that started the whole madness. We would like to lower the carbon footprint of the United States. Why do we want to do that? Because we want to be in the family of civilized nations, right? Isn't that what we hear? Okay, so to be in that, you want to lower your parts per million of CO2 in your air. Today, I think you're getting up there in the 700, 750 parts per million. You want to bring that down to 300, 400 parts per million. And if you don't do that, what's going to happen, according to 9 out of 10 scientists on climate change, this is like Trident chewing gum, right? 4 out of 5 dentists. And so 9 out of 10 scientists are saying that this will cause major swings in the weather, and you're going to have a problem living on this planet. So whatever your personal belief may be about that concept doesn't really matter. Bottom line is we're moving forward with it. So you'll never find out what my personal opinion about it is. But I'll tell you that it's important to get on this bandwagon. Because if you don't get on the bandwagon, you're going to be disenfranchised economically, you're going to be marginalized, and then a lot of your creativity will go to waste. So it's important that whatever your personal opinion about global warming is, don't let that get in the way of getting into this smart grid business, because this is about employment and it's about growth. Okay, because there's some very good things that are going to come out of the exercise, such as electric transportation, such as better renewable sources of energy, more energy efficiency, and all these good things will come out of it. Much like the Apollo program brought a lot of electronics into our society. So think of it from other perspectives. Don't just look at carbon as the final arbiter on this. Okay, so we're seeing that if we set a target of an 83% reduction in our CO2 levels from the 2005 levels by the year 2050, we need to do some aggressive technological investments, and we need to do certain reduction in our demand in order to meet these. It's not all one solution. The answer of this is not the smart meter. Okay, that's the important thing to understand, that this is going to require some work. So let's see what it requires. We did a study called the PRISM study in our environment group, in which we understood that in order to lower the CO2 levels, and this is just showing it up to 2030, that we will have to introduce a lot of technological innovation. We'll have to do some energy efficiency. We'll have to bring in some renewables like wind and others. We'll have to expand our nuclear fleet in order to enjoy the positive CO2 aspect of nuclear power. We'll have to increase the efficiency of fossil fuel plants by making the inlet and outlet temperature higher, using more advanced materials and so on, using gasification of coal and other things to improve that efficiency. And then there's carbon capture and sequestration. Today, 51% of our electricity is produced by coal. We cannot ignore it. We can't just say, well, we're not going to use coal anymore, because our renewable portfolio is in the single percentage points, maybe low teens. And the forecasts are not really that promising. So we have to figure out a way in which to capture the carbon that's produced in coal plants. And so there's a lot of research going on at EPRI and other parts of the country on carbon capture and sequestration, and that's what this is. And then you have the plug-in electric vehicle. That's going to have a benefit. The reason why that's going to have a benefit is that plug-in electric vehicles transfer transportation from a fossil fuel-based way of producing energy to drive the car to the grid. And by putting it on the grid, you can align it with certain renewables that have a lower carbon footprint, or align it with nuclear power, or if there was carbon capture and sequestration with that, with coal. And so you get a positive benefit of transferring vehicles from the current gas and CNG type vehicles to an electric vehicle. And then finally, electro-technologies. These electro-technologies are in industrial processes. A lot of places where today you may be using butane or propane or other ways, there may be better ways using electrical technologies. For instance, I'll give you a very simple example. Large water systems develop bacteria. And the reason why they develop bacteria is because there are particulates in the water that precipitate. And they become the food for the bacteria to eat and grow. And then the bacteria creates a polymer-like covering over itself and protects itself from any biocides that are thrown at it. So the layer actually protects. And so the result is that you're throwing chemicals into the system, and it's still not killing the bacteria. And the result is that the bacteria then produces SOx and NOx, sulfur dioxide and nitrous oxide types of gases, which when mixes with the water creates acid, and it creates what's called microbial-induced corrosion, or MIC. And that breaks these pipes and water systems. So in large coolant plants, where millions of gallons are being circulated, imagine what havoc this can play. So what an electrotechnology can do over there is, there are technologies now available which act as a capacitor. And if you put the capacitor in the water, it separates the charge, and there's something known as a zeta potential. And what that does is it takes the impurities and puts a lot of charge around them. And so when two impurities want to get close together, they don't. They repel. And so they don't precipitate. And so the whole microbial-induced corrosion is not created because the charges are separate. So here's an example of an electrotechnology that, when implemented in a water system, could save tons and tons of chemicals, the labor, the acid backwashing that you have to do, and so on. So there are so many things in industrial processes that we could do by moving to electrical technologies. And that's the key thing to understand here. So if you look, you marry all of these technologies, and then you get the favorable CO2 picture. That's key. There's no one solution. It's not just a bunch of wind turbines, avoiding bats. Okay? That's not what this is all about. And I'll talk about bats and turbines in a little bit. Okay, so there are certain assumptions that we made, and the assumptions are that if we took the Energy Information Association's forecast, which was the previous diagram, and we see that if we made certain aggressive investments in nuclear, in plug-in electric vehicles, in carbon capture and sequestration, we could do better than the EIA estimate on CO2, meet our target, and have that low-carbon future that we're talking about. But it's not going to happen unless we make concerted effort in investing in specific technologies. Technologies that today are not very mature. They need investment, R&D money. This is not just about shovel-ready projects. Okay? This needs the help of universities, of national labs, and research organizations to come together to address these issues. Whether it is carbon capture and sequestration, which has a lot of issues that need to be worked out, whether it is storage, getting better storage so that you can leverage more of the intermittent sources like solar and wind, whether it is going to the next generation of nuclear power plants, the third generation, which have better the fuel pieces, the uranium dioxide, instead of having pellets, they are completely self-contained and they don't need that zirconium hydride cladding on them. New technologies that will help smaller size nuclear power plants. We're talking 250 megawatts, 500 megawatts, as opposed to 1.4 gigawatt. So then you can then put them along a bus and you can add them and increase the capacity. So these are some of the novel ideas that we're talking about, where we're bringing it down to a level where a utility can afford them. Today, it's very difficult for a utility to afford a new nuclear power plant. Even if they made Sierra Club happy and everybody happy, their balance sheet cannot support a $6 or $8 billion plant. So they're thinking of pooling together. 2, 3 utilities come together and say, okay, we've got the balance sheet. Now we can take the risk of building a new nuclear power plant. So it's not so much about radioactive waste as Jane Fonda would like you to think. It's more about accounting, economics. It's a lot of money, 6, 8-year commitments. So we got to think about that. So if we made these investments in technology, we could address that CO2 problem. So we have a series of projects that address all the different parts of that spectrum that I showed you. And there are a series of individual initiatives that are called smart grid demonstration, for instance, energy efficiency demonstration. And we have created a series of demonstration projects at EPRI to address those issues that we showed in the PRISM study, to show that we're not just talking the talk, we're walking the walk also. Because this is where you find out exactly what the state of readiness is of the technologies. You cannot do it with just PowerPoint like I am. Okay, you have to back this up with real experiments, real results, which is great opportunity for graduate student projects, senior projects. Partner with the Lawrence Berkeley Labs, the EPRIs, and other organizations, and work with us. I think that part of the DOE money is meant for this. There's one part for services type projects, like what you saw, the tranches being given out, the $3.5 billion. But there's a portion for R&D also. It's granted it's small compared to the shovel-ready stuff. But we need to keep pushing on DOE to tell them that we need more money to do this kind of stuff. Because this is what's going to save the day. Not just by putting a bunch of meters. Because the meters are not going to reduce your carbon footprint, by the way. And you know why? Because peak demand is only 1% of the overall time of the year. So how can that reduce your carbon footprint? It won't. But if the meter is then used to invoke more solar, let's say with solar panels and there's net metering going on and you can sell electricity, yeah, maybe then it will reduce the carbon footprint. But just by putting a meter and having automated meter reading, the only CO2 difference it's going to make is during that peak time, which is 1%, or the avoidance of the rolling of some trucks and the pollution that that truck may cause. So that's not the answer. Okay? That's heading in the right direction, but there's much more to be done. What is the smart grid? Well, in our NIST project, we defined what the smart grid is. The smart grid is basically all aspects of the production, transmission, distribution, and end use of electricity in a networked infrastructure. When I say networked infrastructure, I mean that there is a series of sensors in different parts of the grid that have a communication network that's connecting them all so that the different parts of the grid are aware of each other's presence and state. That is not the case today. Today, most utilities have great visibility up to the substation. In other words, the transmission line up to the substation. But when you go into the distribution network, mostly Ohm's law works. V equals IR. The electrons have no brain. They just look for the direction of lower potential, and they roll in that direction. That's why they don't call it a smart grid today. You just got a series of mechanical or electromechanical systems that move electricity to different sections. So you say, I want to energize this part of the grid, or I want to energize that part of the grid. And you use circuit breakers, basically, to do that, switches, essentially, to move electricity around. But the electricity in itself, it's not like a packet, an IP packet that has a source and destination address and says, I know where I'm going in the packet itself, and I just talk to each intermediary router to tell me where to go. We're not there yet with electricity. Electricity still uses very traditional ways. I liken it to the way water flows in Bangladesh. It comes off the Himalayas, and it looks for any place where it can roll, and usually over villages and towns and stuff, but unfortunate. But this is one of the biggest problems. And electricity kind of flows like that. It looks for a lower potential, and off it goes. So we want to stop that madness. Why do I call it madness? It's madness when you have multiple sources of entry into the grid. Then it becomes madness. As long as you have the traditional model of a central plant producing electricity, it's easy. You just look for the lower potential and you slide down, no problem. But now imagine if there are large wind farms and solar farms, and you say, I want to connect this at the transmission level, at the substation level, at the distribution level, then it's madness. Because Ohm's law doesn't know what to do anymore, because you've got a source of energy coming in at a lower potential, and it's trying to push power into your system. So for those of you who are electrical engineers, know this well, that you need to be careful that you don't create instability, the phase of the electricity, because it's an alternating current, right? So shifting of the phase is not good for a lot of industrial processes. It's inconvenient in homes where you see the fluctuating light and stuff. But for industrial processes, it's even more sensitive. So if you throw the phase off, you can ruin a lot of the industrial processes. So you got to be very careful about maintaining tight control on voltage and phase. And that's why we talk about volt-var optimization. And we'll talk a little bit about that a little later, about what networking the grid does. What benefits does it create? So you have these 7 domains of the smart grid, and we call them domains because within each there is a whole set of environments that need to be networked, and there are systems in each one of them that need to work together. So we'll get into a little more detail now. Here we go. That's same, you see how? You see? This is for the cocktail party. This is for the classroom. Now, what we have here is a series of sub-environments within a domain, and the arrows that, or the lines that are connecting them, show that those systems need to talk to each other. By talking, I mean exchanging information. So they need a network. They need the whole 7 layers of the communication stack, and they also need a semantic layer, a layer that defines the language by which they will exchange attributes and values. How many of you have heard of the Simple Network Management Protocol, SNMP? All right. For all of those of you who haven't heard about it, it is the way in which networks, IT networks today, are managed. So when you get on the internet and you go to www.something, behind that www is an IP address, and to get to that IP address, you need a network, a series of networks that are connected and can pass your data across. So the SNMP protocol manages all of that to make sure that all the links are reliable so that you can reach the destination. We will need something similar in managing the smart grid. I'm saying similar, but not exactly SNMP, because the protocol, in the way it's implemented today in IT networks, keels over at about 50, 60,000 nodes. And so when you have millions of nodes, you need something more scalable. In other words, with a lighter client, more scalable. And we're working those things out in the IEC working groups to figure out what that network management would look like. But you can begin to see that this is complex. You have many, many systems, and you need many, many standards in the different parts for them to interoperate. Because you don't want to become vendor specific. You don't want to lock down to a specific vendor. So here's where the hype goes away and reality strikes. This is, as I said, job security. Each aspect of it requires weeks and weeks and months of work to work out all the 7 layers of the communication. This is a flat diagram. There are actually 7 layers in there for the physical, MAC, network, transmission, presentation, session, application, all of those layers, and then the semantic layer, the language that rides over it. So this whole smart grid is being cataloged right now through the UCA, the Utility Communication Architecture International User Group, under Open Smart Grid. We are cataloging all aspects of this. Okay? Now for the pretty picture. So here you have the different parts of the smart grid, as I show you, and showing that a communication network needs to connect all of this together. So the hype is, it's there. The reality is, it's not there yet. And the reason why it's not there yet is because vendors for years have created proprietary standards, what they call de facto standards, and they don't talk to each other. And so when you have somebody giving you a distribution system, someone else giving you a transmission system, some other vendor over here, there needs to be an ability to talk back and forth, and we don't have that today. So we're working on building that language and making sure that there are standards for interoperability. Okay, let's look at the back end. So there's got to be tons of data that's going to be generated, right? You have all these sensors that are gathering voltage, current, phase type data. You have energy usage information coming from homes. That all needs to be kept somewhere. So there are data centers that are being built to support just the smart metering work that's going on. We need to gather that data and be able to poll it and produce reports from it. You may have heard of the Google initiative, and Microsoft is also looking at this whole power meter. You may have heard of that, where they want to get the energy usage information and be able to publish it for the consumers so that they can carry it on their PDA and be able to see how much energy they're using. That's not an easy task. That's very complex. Forget all the legal issues with privacy and everything. Let's say that we're living in a utopic world where privacy is not an issue. Just the data collection, sorting, parsing, and reporting is a mammoth of a job, because you're looking for that needle in that haystack. There are tons and tons of data that's going to be collected. It's not just meter reading. You're going to collect all the meter stats, and all of that is going to come back. So we have to architect it properly, and we have to create a common language on the back end so that systems can exchange data seamlessly with each other. You don't need custom integration. So companies like the IBMs and the Capgeminis and Accentures, they make a living off of this, right? For days and days, there are consultants sitting, working, typing away till the wee hours of the morning. What are they doing? Taking application M and application N and trying to find a way to map them together so that they can seamlessly exchange data. But that's a one-off integration. So if you have M and N, it's called the M by N problem. You got a bunch of servers here and a bunch of servers here. Think of the matrix, how many integrations you have to do. That's a lot of W-2 forms, a lot of H-1 visas, right? So it is. It's a lot of H-1 visas. Been there, done that. So the point I'm trying to make is that it's not scalable. We can't create a smart grid with custom integration. We need to have open, standards-based systems that can exchange data independent of who the vendor is. So the question is, what happens to intellectual property? You know, yesterday, vendors used to covet the intellectual property by making it more proprietary, more esoteric than ever. We can't afford to do that. So in the new paradigm, intellectual property can be there for things beyond interoperability. In other words, much like what Linux did to operating systems, right? It forced the Microsofts and the Solarises and others to bring their price point down to make it more affordable, but they opened up a lot of their operating systems so that people could write applications to them because Linux would have them for breakfast otherwise. So think about these things. Open source type protocols are just on the horizon in this business. We can't make money off of proprietary things here. What we need to make money off of is customer service, is providing a quality service to the consumer. That's where the product differentiation is going to be. It's not going to be in the technology. Everybody knows Internet Protocol. Everybody knows the Common Information Model. All you have to do is pay $3,000 and you can get the standard. So that's not where the differentiation is going to come. So the difference between hype and reality here, again, the hype is you're going to make billions. The reality is you may make tens of millions. Okay, billions, I've heard many, many adventures like that. Nuclear fusion, which I was a part of, didn't go anywhere. Network management, I was a part of, didn't go anywhere. Fiber optics, I was a part of that, didn't go anywhere. You know, over and over again, I've been in multi-billion-dollar schemes that didn't go anywhere. So now I'm here to tell you it's not going to happen again. Okay, not to me. I'm going to make sure that we'll keep our reality check on and that we do it in a managed way. Because there's no point taking a bunch of hard-earned money from people, putting them in equities, and then having the value drop. That's a crime. I mean, we keep talking about terrorism. I think this is the ultimate terrorism, is you take hard-earned money of people and through speculation, and then drop the value of the companies and they lose everything, like what we saw in 2001. That is bad. I think that we need to have laws against that. Okay, so, yeah, I mean, it's speculation. So, but if you remove the hype, you understand that you can do this in a managed way, get the desired result without making some people multi-billionaires and others relegating them to poverty. So coming back to the subject of backend, it's important to create on the backend bus, an enterprise service bus, what we call ESB, or a service-oriented architecture, an SOA, so that at the application layer you can exchange information between various applications, such as outage management system, customer information system, then you have meter data management system, fleet maintenance system. All of these systems on the back end need to be interconnected. So let me give you a little case study. You've got a meter that's connected to a house that caught fire. What should be the first thing that we should do as a utility? Call the fire department. But as a utility, I mean, that's what the customer will do. He'll use his cell phone, call 911, right, and get that. But what should the utility do? Shut off the electricity. Because a house on fire, you're providing fuel to the fire by letting electricity run into it, right? I squared R, a lot of heat. You're just adding fuel to that fire. So you want to stop that. How would you know the house is on fire? You wouldn't know it unless someone called. But if you have a solid state meter, and hopefully it's in some fire enclosure, it's going to sense that I've lost load dramatically, you know, because the house caught fire, the wire burned down. Something is fishy. So there should be an alert that should go back to the utility saying, I'm in a state of alarm as a meter. And so the first thing that happens in that situation is you put a lock on the flow of electricity. You don't keep energizing that link. The second thing is that you should be able to extract the data from the meter in order to see the history to that event. Maybe there's some information that we need to know. You know, for insurance purposes, you need to know whether it was an electrically generated fire or was someone just throwing matches in the air. What was it? So if it was anything to do with electricity, usually it's associated with an increase in current flow, right? You put a bunch of things on a wire that wasn't rated correctly for it. So there's a lot of information, meaningful information you can pull out. That needs to go through the meter data management system to the outage management system. That outage management system needs to be connected to the customer information system, which is connected to a GIS system, so that you know exactly where that house is located and who's in the premises. Maybe there's some senior citizen there, maybe someone who needs help. You know, all that information will be available to you. And then you would have a fleet maintenance system that would do a smart dispatch with exactly the tools you need, because you know the meter, the version of the software, everything on it. See what an interconnected thing can do? Here's a case study that would save tons and tons of money and a lot of labor that would be involved in, you know, very manually intensive work today. But connecting them all like that, it could work like this. An example is JEA, Jacksonville Electric Authority. They've had this for the last 10 years, this whole integration on the back end. And the reason is because they went to the Itron drive-by type of meter reading, where they had a truck going around and they'll capture the signal from the meter. So they needed an automated way of creating bills for consumers 10, 15 years ago, and they did it. So today we talk about smart grid, but there are real utilities who have automated systems on the back end, and we could learn from them. It's not just from PG&E and SCE and SDG&E. You know, those are nice. We could go to them, but there are other utilities that have done far more work out of necessity. A lot of co-ops have done that, you know, that work in very rural areas. It's NRECA is the organization, National Rural Electric Co-op Association. They have many customers who have this all worked out on the back end. And there's a protocol called multi-speak, which has helped integrate this back end. 8? Wow. All right. So here it's showing that you have some legacy systems that require an interface, like protection and SCADA, and there are others that are so new that you can integrate them directly into this bus. You could do that. For instance, for those of you who have worked with mainframe computers, you realize that there was a time, how many of you have heard of SNA? IBM's SNA. Okay. So, all right. So here's a real legacy protocol, right? And it had its own addressing scheme, its own hierarchical structure of systems. There was a level 2, level 2.1, level 4, level 5, right? I'm dating myself now. But they had this hierarchical system, but it was all very proprietary, all IBM stuff. Then IP came around, and they said, oh, now we have to deal with this beast. So they first kept it out, and there was this point of handoff between IP and SNA. But today, there's native IP in legacy systems. In other words, the server that carries the mainframe application has an IP address in itself. This is how slowly it has migrated. And we'll see the same thing going on here with the applications, that we'll move to this bus-like architecture. As I mentioned about GIS and OMS, all of this needs to be integrated. This is like the IQ of the smart grid. If you don't have this, you don't have a smart grid. All you have is a bunch of expensive solid-state-based hardware. You need to have logical connectivity to increase the wisdom and the strength of the smart grid. How you make real-time decisions is based on how well you integrate all of this. And here is a customer premise. I know a lot of you have spent a lot of time and energy thinking about displays and things like that. And have you noticed that I've talked very little about it? Because this was about demystifying the smart grid and separating hype from reality. The reality is that the transmission and distribution part of the grid is where the lion's share of intelligence is needed today to make the smart grid work, far more than the customer premise. And I can say that running a customer premise research program, that a lot of what you're hearing about smart meter and the toaster is going to do a denial of service attack to the refrigerator, and there's going to be a firewall at the meter, and it's going to be like Fort Knox, and nothing will be stolen, and baloney. Be prepared that meters are going to be compromised. No matter how much security you put on it. You can put elliptic cryptography on it. You can put AES 256. It does not matter. You give physical access to a bunch of tinkerers, they're going to find a way around it. It's that simple. Somewhere in the circuitry, it's going to be unencrypted, and they'll find it, and they'll put their little tweezers, and they'll put their data in there. Because how do I know this? Because we are already doing it at EPRI. We can enter a board where at a place of our choosing and put things into it. And we have white hat hackers who do it for a living. So the charm is not in securing the customer premise. The charm is in doing good intrusion detection and prevention. That once someone has compromised the system and they're trying to ride up the jugular vein into the meter data management system, that at the access point, before they can even compromise that, that alert has gone through maybe some cloud computing system back to the NOC and saying someone is trying to get in from this meter in an unauthorized way, stop them. That is going to be much more intellectually challenging and more realistic than this idea that a lot of vendors are trying to pitch, that I've got a secure meter. So what? The first time someone's going to break into it, all bets are off. So you don't want that way. You know, where in the United States, the way we do immigration, we have this big guy sitting at the airport who says, I want all your visa, everything information. And then once you go in, it's free reign. You can go to any state, do whatever you like. Nobody bothers you. We can't have that in the smart grid. We have to have a series of challenges at every step of the infrastructure so that the hacker just gets frustrated and says, forget it, I'm not going in there. And that's part of that design. So you can see that these are very complex environments. There's industrial, commercial, residential. Our hope is that we'll create a building automation system which will be universal to all three sectors. So from a utility perspective, it doesn't matter what sector you're dealing with. You can talk that same language across all sectors. It's very important to bring the price point down for the technologies. You don't want to, as a vendor, produce a product and wonder whether it's going to be used in a house or a factory or a mall. That's not the right way to do it. Create a universal language, and it should work and play at any place. I spoke about the NIST project. We are currently in phase 2 and phase 3, where we have built these smart grid interoperability panels. I would highly recommend, whether you are in the faculty or you're in the student body here, or you are an entrepreneur, to get involved in the smart grid interoperability panels of NIST, of an area of your choosing, whether it's in the customer premise, transmission, distribution, generation, cybersecurity, doesn't matter, but get involved. You are one of 21 industry stakeholders that are defined in the project. So if you don't show up to the party, it's your fault. Okay, so get in there, contact NIST, find out www.nist.gov/smartgrid is the website, get involved. Otherwise, don't complain, because what you're going to get is the result of what the group decides to do. This is very democratic, by the way, because we created it. So we made sure that it was not just the luxury of a few people. So that's important. There's a series of priority action plans of NIST. You can get involved in any aspect of it. Electric transportation is hot in the Bay Area. You can go for that. You can get into the IP for smart grid. You know, if you're into the internet protocol, you could get into any of these aspects. And I have left this presentation here, so you can share it with the group, and they can decide which one they want to get into. There's also a 15, and the 15 PAP is a new one that was created, which takes the G.HN, which is a home area network protocol that's being introduced by ITU and AT&T and others, and how it would be harmonized with HomePlug. HomePlug is the power line-based protocol that they're thinking of using for charging electric vehicles, for instance. Okay. So I just want to wrap up my presentation with 2 slides to show the smart grid demo project that we're currently doing at EPRI. We are involved with a series of utilities, and I'll show you their names in just a second. But we're doing distributed generation, renewable generation, storage, demand response, and we're checking multiple levels of interoperability to show the utilities how mature the smart grid technologies really are. And then these are some of the utilities that are doing this project with us. We work on their sites. We do the project management to help integrate all those sources of energy into the grid to see how stable the grid remains after that. Europe, as you know, Denmark and other countries have gone much higher in percentage of renewable than we have. And they can do it because they don't have as tight a tolerance on the voltage as we do. So in our industrial processes, when we do 60 cycles, we mean 60 cycles. If it goes 59 point something or 61 point, our industry doesn't like it. But in Europe, their industrial processes have kept a wider margin for handling voltage swings. So they can afford more impurity in their grid. And I say impurity because intermittent sources of energy, wind and solar, create impurity in the voltage, current, and phase situation in the grid. So to offset that, you either have to run peaking units, which destroys the whole carbon picture, or you need extensive storage, which is still very expensive. The rest of my presentation I'm going to leave because it involves projects that we're doing at EPRI in our base program. You can read it. You can reach me. I'm all the way at the end here. I'm not going to bore you with all this, but this is the nerdy stuff. But I bring it because it's educational, as you can see. Yeah. And that's my contact information, so I guess we'll open it up for questions now. All right. You're going to, okay, you'll moderate.
So at the beginning you said that this network is not going to be a master-slave relationship. We talked about information going in both directions. What about control? Can you speak a little bit about to what extent might we expect some sort of decentralized control? That on the second to last slide that you showed, there was all of the data seems to be going to a centralized.
That is meant more for if you have just a utility serving a bunch of customers, then you would have that centralized place where you would bring the data. But now that we're going to have independent power producers, they're going to have their own reservoirs of information. So think of each player that's coming into this as having this infrastructure, and that there needs to be a way by which data can be exchanged between them also.
And what about control?
Okay, in terms of the control, for the near term, we can see the investor-owned utility, the large utility, basically controlling the grid for their customers. And they will tell the independent power producers, I need so much energy from you at this time. But the independent power producer has to expose their assets so that the request is realistic. Because you can't just have a black box type situation. And that's why we're trying to build this language called the Common Information Model to be able to go past the integration point from the IPP and actually look to see how many wind turbines they have or how many solar panels, whether they're available or not.
As you're developing the sort of open source concepts and language and the technical standards portion of it, where does the policy debate intersect with this in terms of deployment and the bottom line funding we pay?
Right. Okay. There are a lot of legal issues that smart grid is creating. One of the biggest issues is that of privacy. You have so much data about the lifestyle of people that's being collected by utilities through the 15-minute interval. And the next level of development, we're actually going to have sensors that we'll put on the wire itself. And through the signatures that all the plugged loads create on the wire, we could tell which appliance was using the electricity when and how long. So you know whether you use the toaster up to 3 or 2 or 4. Do you like your bread browned or you like it white? You'll know to that level of granularity. So I tell people that it's going to be a lot like the way healthcare and the way the banking industry has dealt with it. That they are the custodians of huge amounts of very, very private information. But as a result of a set of agreements with the customer, they divulge some information and they withhold other information from external parties. And it's really that, so that's one dimension. The other dimension is, even if the utility were to hoard this data and remove the particulars of the individual customer from it and have aggregate information on different demographics, that cannot be traded according to some FERC regulations. Because if you provide that, let's say, to a party that's involved in energy trading, they would have beneficial information where it can give them an advantage in the trade because they know how much electricity is needed at a certain time. So even though the customer may sign off and say you can do whatever you like with the data, that still doesn't give the right to the utility to aggregate that and give it to people, third parties. So there are rules on this issue, and we are working with FERC on that.
I'm talking about the policy debate in terms of rate.
Oh.
Policy in terms of the dollars to make these investments and who actually is going to pay the upfront cost, which will have to be incurred before the benefits are realized.
Right. So what I'm recommending to NIST and to DOE and others is that let some of the stimulus money be used for this purpose, because this dollar will pay itself off many, many times, as opposed to just putting it all in the deployment of meters. Because meters by themselves are a dead end unless you deploy all the technologies that can be enabled by that infrastructure. So it should not be this unbalanced approach. Now, in terms of rate paying, I think that the utilities need to make the proper case. So for instance, the solar panel today is largely what we call a Ponzi scheme, right? Is Eric here? Where is Eric Westhoff? Is he here? Okay. All right. And why do I call it a Ponzi scheme? Because you got the very wealthy that can afford solar panels, and they're given a subsidy by the utility, which is then paid by everybody else who can't afford the solar panel. That's the reality of solar panels today. So we need to change the way we do things so that we are not taking money from the poor people and giving it to people who can afford it just to have a subsidy so they can get the solar. Then they get to sell the electricity and make money off of it, while the poor people then have to pay higher rates because they're getting solar power now at a much higher dollars per kilowatt hour. So it's not set up right yet. So I agree with you that we need to change the regulatory framework in order to make all of these technology investments wise or feasible.
Got time for one more question.
Oh.
And a read. One more.
Yeah, when I was in New Zealand, I saw lots of ripple controllers turning on and off water heaters and other non-essential loads from the power company's signal. Is that something that we have in the U.S. and how much of that?
We do, and it's very unpopular here. Here it's you got your woman, you got your car, you got your house. This is very much a country of my thing, my beer, my chips, my plasma screen. So our mentality is different. I'm serious. I mean, I've lived here 30 years. That's what we do. So, and anytime you disagree, I'm ready to secede the union, as you heard after the 2008 elections. So we got to be careful. There was a utility, and I'm not going to mention its name, that had this program, and the first hot day that they had when they tripped the AC, 11% of the people in the program wanted out. The first instance of it. They were ready to take the 25% saving, but the day they had to sacrifice because it was a hot day on Sunday, and can you imagine playoff Sunday and someone says no air conditioner, so no party in your house? I mean, serious social implications. So yeah, so this is why we are so dependent on this two-way system. It's giving this nice touchy-feely feeling like I can tell you when I want it, you can tell me when I can't have it, and then everyone is like okay with it. But if you tell me, then I have a negative reaction right away because I want choice, even though most will not exercise it.
Coming from New Zealand, I could say I've never had a cold shower because of ripple control. I mean, using the water as a storage tank as well. So,
Yes.
Yeah, but, yeah. Anyway, that's probably...
For more, please visit us at stanford.edu.